Hello everyone and welcome you all in this next class, and here we are going to see the topic on the types of sections. So in the previous class I have discussed on XU, which is the actual depth of neutral axis, and XU limiting or XU max, which is the maximum or limiting depth of neutral axis. So let us have a fast recap of what we have discussed. If this is our cross section of the beam and all the dimensions are shown here, so how do we calculate the limiting depth of neutral axis? XU lim कैसे calculate करते हैं? Based on assumption, both the concrete and steel reaches its maximum strain value simultaneously, and from the similar triangle we can equate 0.0035 divided by XU limiting is equal to 0.87 Fy by ES plus 0.002 divided by d minus XU lim. And if you simplify this equation, we arrive at XU limiting by d is equal to 700 divided by 1100 plus 0.87 Fy. And the ratio of XU limiting and effective depth is a constant. It do not depend on the characteristic of concrete or the cross section of the beam. It only depends on the grade of a steel, Fy. And this table is also listed in the IS 456 that we have seen. So in any problem that you encounter, I would suggest you that your first step should be always to calculate XU limiting. And what you have to do first is you have to calculate the effective depth. D is equal to gross depth minus clear cover, and the ratio of XU limiting and effective depth can be obtained from the table in the IS 456, or you can remember also these three values. Now after calculating the limiting depth of neutral axis, our next step should be to calculate the actual depth of neutral axis XU. And how do we calculate it? We just have to do one thing. We have to apply the equilibrium of forces. Total compressive force is equal to total tensile force. And we have very elaborately explained all this strain profile as well as the stress profile, and calculated the value of C1 for the rectangular block and C2 for the parabolic block, and then calculated the total compressive force, and the depth of compressive force from the top is also calculated from the area moment theorem. So these calculations of the parameters of a stress block we have already done, so I'm not going to explain it here. You can just have a look at here in brief, and after this we equate the total compressive force equal to the total tensile force, which is equal to 0.87 by AST, and equating these two forces gives us the value of actual depth of neutral axis. So the value of XU is 0.87 F by AST divided by 0.36 FCK times B. Okay, but of course this formula will be valid only if the actual depth of neutral axis is less than or equal to the limiting depth of neutral axis. And if in case the actual depth of neutral axis exceeds the limiting depth of neutral axis, which we don't do because that section is over reinforced section and that is prohibited as per the IS 456. But if such cases happens, then how do we calculate the depth of neutral axis? We have to use the strain compatibility. So that is the only way which is left with us. Now any beam or flexural member has some capacity to resist the bending moments. So the capacity of any flexural member in terms of its bending moment is named as ultimate moment of resistance, and it is denoted by mu. And the calculation of mu is very easy because it is the couple generated by the C and T with the lever arm d minus 0.42 XU, and we can calculate either of the ways from the compression side or the tension side. And the calculation formulas are simply the compressive force multiplied by the lever arm or the tensile force multiplied by the lever arm. So this is very easy to calculate. And then we also calculate the limiting moment of resistance, and this is represented by mu limiting. Now you will say, what is the difference between mu and mu limiting? Mu is the ultimate moment of resistance corresponding to the actual depth of neutral axis. When we calculate ultimate moment of resistance mu, then we use actual depth of neutral axis XU. And if we have to calculate the limiting value of moment of resistance mu lim, then of course we have to use the value of XU limiting. Okay, so the calculation of mu limiting is very easy. We just have to multiply the compressive force with the lever arm, but here we have to use the value of XU limiting in place of XU. And after putting all these values, we arrive at the formula mu limiting by FCK BD square is equal to 0.36 XU limiting by D into 1 minus 0.42 XU limiting by D. And the formula which we have arrived to may be appearing difficult to the eyes, but you need not to remember them, because if you have understood the concept, you can easily calculate it. And the value of XU limiting by D is a constant for different grades. Similarly, the values of mu limiting by FCK BD square is also a constant. Alternatively, we can also calculate the value of limiting moment of resistance mu lim from tension side also, and we just have to put the value of XU equal to XU limiting. So now let us discuss the different types of sections of beam. So we are constantly discussing XU and XU limiting. So I am going to do a comparison of XU and XU limiting. This is the cross section of the beam, and this dotted line represents the maximum depth of neutral axis XU limiting. And if in a case we get the actual depth of neutral axis less than the limiting depth of neutral axis, so in such cases the steel bars will yield first and will reach its design strength 0.87 Fy very easily, and the concrete will remain safe, it will not be crushed. In such cases, the stress in the steel bars is equal to 0.87 Fy, and such a cross section is said to be under reinforced section. See, in under reinforced section, what happens? Steel has yielded first and the concrete is safe. So what will happen at the failure? The steel will start yielding, and steel is a ductile material. So the steel will undergo plastic deformation after yielding is reached, and the beam will start deforming, and in that case we will get sufficient warning because the RCC element will become ductile, and that's what we want. We want sufficient warning before the actual failure may occur, so that we may take the required precautionary measures against these failures. But there may be a case in which our actual depth of neutral axis is exactly coinciding with the limiting depth of neutral axis, and this is very rare to obtain. Most of the time this is hypothetical case. We try to design for the under reinforced section only, but if in case it happens, then we have to use the value of XU equal to XU limiting, and in those cases obviously we have to use the value of XU equal to XU limiting, and the stress in the steel bars will be again equal to 0.87 Fy, and such a cross section of the beam is said to be the balanced section. Now comes the worst case, when the actual depth of neutral axis exceeds the limiting depth of neutral axis, which can't happen and which is also not recommended as per the IS 456. So in such case, even if we increase the load, the steel is not going to yield. But the worst thing that is going to happen is that the concrete will reach its ultimate strain before the steel actually yields. So in this case, the stress in the steel bar is not equal to 0.87 Fy. It is less than 0.87 Fy. And such a cross section of the beam is said to be over reinforced section. So these are the three very important and different cross section of the beam, that is under reinforced section, balanced section and over reinforced section, depending on the value of XU in comparison with the limiting value of XU. So as I told you, in any calculation, first of all calculate the value of XU limiting and then calculate the XU and compare. If the value of XU comes less than the XU limiting, so our section is what? Under reinforced section. In case of under reinforced section, we have to calculate the actual depth of neutral axis using this formula, and we know the steel has been yielded, so we can calculate the value of ultimate moment of resistance using this formula, and in this formula we have to put the value of XU, actual depth of neutral axis. Okay, if in case you obtain the actual depth of neutral axis equal to the limiting depth of neutral axis, which is very rare, so such a cross section is said to be balanced section. And in case of balanced section, the ultimate moment of resistance mu will also be equal to mu limiting. because XU is equal to XU limiting. So the value of ultimate moment of resistance mu, which is equal to mu limiting, can be calculated by using either of these two formulas. Alright, and here we can always use the value of XU limiting, and we can calculate the value of XU limiting very easily if we are given the grade of a steel and effective depth. If in case the actual depth of neutral axis we obtain exceeds the limiting depth of neutral axis, which is going to be a over reinforced section, so in that case we are not going to use the value of XU, alright, because XU is limited to XU limiting, and in that case also mu is not calculated. In fact, in over reinforced section mu remains limited to mu limiting. Can you understand this? Because XU cannot exceed XU limiting, so how can mu exceeds the mu limiting? Because these are the limiting values, and that is what the limiting capacity of the cross section. So if you have concluded that your cross section is over reinforced, after doing comparison between XU and XU limiting, you need not to calculate the value of mu. You just calculate the value of mu limiting. But unlike earlier, where mu limiting was calculated either from the compression side or from the tension side, in this case we can't calculate mu limiting from the tension side because we don't have the idea of stresses in the steel. So we have to calculate mu limiting from the compression side only, and that is equal to 0.36 FCKB XU limiting multiplied by D minus 0.42 XU limiting. So this is how we calculate moment of resistance in most of the analysis problem of singly reinforced beam. So whatever I discussed in this slide is the crux of calculating the values of moment of resistance, and that is what we have to do in most of the analysis problems of singly reinforced beam. So in any analysis problem of singly reinforced beam you encounter, you just follow these tips and you will surely arrive to the exact value of moment of resistance, and that is what is all about the types of section and the calculation of moment of resistance. So this was all, and I would like to interfere, and in the next video I shall try to discuss some numerical problems also. So stay tuned and stay safe. Thank you.